solutions contain relatively high concentrations of a weak acid and its conjugate base. When small amounts of acid or base are added to the solution, buffers react with the added acid or base and resist large changes in pH. Many biochemical reactions require specific buffers to work properly. Therefore, making buffer solutions is an important laboratory skill in biochemistry. Okay, so for a brief review of how buffers work, let's look at a generic buffer that consists of a weak acid, HA, and its conjugate base, A-. If an acid, H+, is added to the buffer solution, the conjugate base A- will react with it. We can write the balanced equation for this acid-base neutralization reaction as A- plus H+ gives HA. If a base, OH- is added to the buffer solution, the weak acid, HA, will react with it. We can write the balanced equation for this acid-base neutralization reaction as OH- plus HA gives H2O plus A-. Therefore, a buffer resists changes in pH because it contains both an acid, HA, to neutralize added OH- ions, and a base, A- to neutralize added H+ ions. There are two ways to make a buffer solution. The first way starts with an aqueous solution of a weak acid, HA. Since weak acids have a low percent ionization, in aqueous solution, most of the weak acid will stay as HA, and only a small percentage of HA will turn into A-. So, to represent an aqueous solution for our weak acid in our particulate diagram, we start out with 4 HA molecules and 0 A- anions. Water molecules are left out of the particulate diagram for clarity. Next, we add a solid salt, NaA. When NaA dissolves in water, it turns into the Na+ ion and the A- anion. So, if we add 4 particles of NaA to the aqueous solution of HA, they will dissociate and form 4 Na+ ions and 4 A- anions. Buffers work the best when the concentrations of the weak acid and its conjugate base are equal. Since we have 4 HA molecules and 4 A- anions in solution, we have a good buffer solution. There are also 4 sodium ions present in the solution. However, sodium ions don't react with water. Since the sodium ions don't react with water, they don't affect the pH. The second way to make a buffer solution also starts with an aqueous solution of a weak acid, HA. However, this time, instead of adding a salt, we'll add a strong base. This time, let's start with 8 HA molecules in the particulate diagram. Our next step is to add an aqueous solution of sodium hydroxide. Sodium hydroxide is a strong base that dissociates into sodium ions, Na+, and hydroxide ions, OH- when dissolved in water. OH- reacts with HA in an acid-base neutralization reaction to form H2O and A-. So, in the particulate diagram, if we pour in a solution that contains 4 particles of OH-, the 4 OH- ions will react with the 4 HA molecules to form 4 A- ions. So, after the acid-base neutralization reaction is complete, we're left with 4 HA molecules and 4 A- anions. Since we have equal amounts of HA and A-, we have a good buffer solution. Since we added 4 particles of OH-, we would also have 4 sodium ions in the solution. Notice how the buffer solution that we made the second way is identical to the buffer solution that we made the first way. They both have 4 HA molecules, 4 A- anions, and 4 Na+ ions. Now that we know how to make buffers, let's look at why buffers are the most effective over a certain pH range. Since buffers work the best when the concentration of HA and A- are equal, let's find the optimal pH for a buffer. To find the pH of a buffer solution, we use the Henderson-Hasselbalch equation, which says that the pH is equal to the pKa of the weak acid plus the log of the concentration of A- divided by the concentration of HA. Okay, so that sounds pretty complex, but we can break it down. Since the concentrations of A- and HA are equal, the ratio of A- to HA is 1 to 1. Since the log of 1 is equal to 0, the pH of the buffer solution is equal to the pKa of the weak acid. If we add enough acid or base, eventually a buffer stops being effective. This is often called breaking a buffer. So let's start with a buffer solution that has equal concentrations of HA and A-. And if we add H+ to the buffer solution, the A- reacts with the H+ to form HA. Therefore, adding acid causes the concentration of A- to decrease, and the concentration of HA to increase. When the ratio of A- to HA becomes less than 1 to 10, buffer solutions break and lose their buffering action. If we plug in a ratio of 1 to 10 in the Henderson-Hasselbalch equation, the log of 1 divided by 10 is -1. So, the pH of the solution is equal to the pKa minus 1. Let's return to a buffer that has equal concentrations of HA and A-. This time, if we add OH- to the buffer solution, the HA reacts with the OH- to form A-. Therefore, adding a base causes the concentration of HA to decrease and the concentration of A- to increase. When the ratio of A- to HA becomes greater than 10 to 1, buffer solutions break and lose their buffering action. So if we plug in a ratio of 10 to 1 in the Henderson-Hasselbalch equation, the log of 10 divided by 1 is 1. So the pH of the solution is equal to the pKa plus 1. These calculations show us that the effective pH range of a buffer is equal to plus or minus 1 of the pKa value. For example, we can consider a buffer system consisting of acetic acid and its conjugate base, the acetate anion. The pKa value for acetic acid is 4.75. Therefore, the range of effectiveness of the acetic acid acetate buffer solution is plus or minus 1 from this pKa value, corresponding to a pH range from 3.75 to 5.75. Alright, now that we understand that it's possible to break a buffer, let's look at the buffering capacity of two buffers using particulate diagrams. The buffer on the left has 4 HA molecules and 4 A- ions. The buffer on the right has 6 HA molecules and 6 A- ions. Since both buffer solutions have equal concentrations of HA and A-, both buffer solutions have a pH equal to the pKa. Even though their pHs are the same, their buffering capacities are different. Since the buffer on the left has a smaller number of HA and A-, if we added enough acid or base, it would take less acid or base to break this buffer. Since the buffer on the right has a greater number of HA and A-, it would take more acid or base to break this buffer. Therefore, the buffer on the right has the greater buffering capacity. Now, let's use what we've learned about buffers to make a specific buffer solution with a pH of 9. The first step is to choose a good weak acid conjugate base pair. An acetic acid acetate buffer would not work because the pKa of acetic acid is 4.75. So the effective pH range of the buffer is, like we learned, plus or minus 1 from 4.75, so 3.75 to 5.75. A better buffer would consist of the ammonium ion, NH4+, and its conjugate base, ammonia, NH3. The ammonium ion has a pKa value of 9.25, so the buffer would have an effective range plus or minus 1 from 9.25, so 8.25 to 10.25. Since a pH of 9 falls within this range, the ammonium ion ammonia buffer is a great choice. Now that we've chosen our buffer, suppose we just so happen to have some solid ammonium chloride and 1 liter of a 0.10 molar aqueous solution of ammonia just sitting around the laboratory. Since ammonium chloride is a source of ammonium ions, we can dissolve a certain number of moles of ammonium chloride in the ammonia solution to make our buffer. To figure out just how many moles of the ammonium ion we need, we start again with the Henderson-Hasselbalch equation, which says that the pH is equal to the pKa plus the log of the concentration of the conjugate base over the concentration of the weak acid. For the buffer that we chose, the conjugate base is ammonia, so we plug the concentration of NH3 in the numerator. The weak acid is the ammonium ion, so we plug the concentration of NH4+ into the denominator. We can also plug in the desired pH of 9 and the pKa of the ammonium ion, which is 9.25. When we subtract 9.25 from 9, we get negative 0.25 is equal to the log of the concentration of NH3 divided by the concentration of NH4+. Since the concentration of ammonia is 0.10, we can plug that in and solve for the concentration of the ammonium ions. To get rid of the log, we take 10 to the power of each side of the equation. After doing a little bit of algebra, we end up with a concentration of ammonium ions equal to 0.18 molar. Now, we can calculate how many moles of ammonium ions that we will need by using the equation molarity is equal to moles divided by liters of solution. Since the molarity of the ammonium ions is 0.18 molar and the total volume of the solution is 1 liter, we need 0.18 moles of ammonium ions. So what we can do is add 0.18 moles of ammonium chloride to the 1 liter of 0.10 molar ammonia solution to make a buffer solution with a pH of 9. Alright, as a quick recap. A buffer consists of a weak acid and its conjugate base. There are two ways of making a buffer solution. The first way is to start with an aqueous solution of a weak acid, and then add a soluble salt that contains the conjugate base. The second way to make a buffer solution is to start with an aqueous solution of a weak acid and then add a strong base to neutralize some of the weak acid. When some of the weak acid is neutralized, it turns into the conjugate base. The effective pH range of a buffer is equal to plus or minus 1 of the pKa value. Therefore, when choosing a buffer, the pKa value of the weak acid must be relatively close to the desired pH of the buffer solution. Once the identity of the buffer has been chosen, the Henderson-Hasselbalch equation allows us to calculate the exact concentrations necessary to achieve the desired pH.